Okay, so in this chapter, we'll talk about processes and threads. And when we say a process or a thread, it's a piece of code, part of your program. That's it, as simple as that. From last lecture, we had an idea about what type of system calls or programs to can be executed in Unix. So we said that there are some process control uh, functions: fork, exit, and wait. This is for the processes. For the file management, we have this group. For device management, we have this group. For information maintenance, we have this group. Communication, we have this group. And then for protection, we have this group. So you will notice that during today's class, I will talk a little bit about the pipe, which is mainly for communication, how the programs are communicating with each other, how the processes are doing it. And then also I will talk about the process control. So it's a theory class, so I hope in the lab you are practicing these kind of things and things are all right at the lab side. Well, anyhow, if you have any difficulties, just send me an email or send me an SMS or inform me, please. Also, from last class, we said that if you have a program, you have a program like this one, and you want to use printf, okay, command printf. This printf command uh, is part of your code, the whole program, and this program is running in the user mode, which is less privileged. There are no much of privileges for you. You have a limited area in memory where you can work. So if you need to communicate with the hardware, you have to switch to the kernel mode, which is the operating system job. It will switch into the kernel mode where it call write function. It will use, it will execute the write function, and the write function is a system call, which is it has the privilege to communicate with the hardware. So in this sense, also today's class, we will focus on the processes and on the threads. We will see how also we can have this kind of relationship. You switch from user mode to the kernel mode, and all of these kind of things happens. But in details, we'll talk about the processes, process scheduling, and we have some concept like the process control block and the inter-process communication. Also, a shared when we have shared memory, uh, what will happen. Uh, so these concepts are important for you. By the end of this class, you'll have to describe and these kind of terminologies, inshallah ta'ala. طيب. So uh, what is a process? It's a program in execution. That's it. That's it. And this piece of program this is a piece of a larger program. So one program might have multiple processes. Okay, that as simple as that. Now the program itself, it is called text section, and it is saved in memory in a specific area. And once it is executed, then there is something called a program counter. Okay, so it counts every step in your program, every process in your program. And if you want to save the data, it is saved in registers. Okay, and we have the stack also, which is it contains a temporary data, like the function parameters, like the returned addresses, like the local variables in your program. It is all saved in something called a stack. And the data section contains the global variables. Okay, and we have the heap. It contains the memory dynamically allocated during runtime. And if you don't remember these kind of things, it is not difficult to understand. Uh, so this is a representation of a memory. So there is the text, the data, the heap, the stack, these kind of things. This is a memory for one program or for one uh, process. Okay, it's a piece of the program. So if this is an example, just for you to understand what is it. So if suppose you have this program, this is a program in C language, okay, and how it is saved in memory. Okay, so the code, the whole code, this code, all of it, it is copied here in this area as a text, and then it is executed piece by piece. So if you want to execute int x and int y equal 15, this is going to be saved in this uh, data area here in this area. Either it is initialized variable like y equal 15, this is initialized data, so y have an initial value of 15. X doesn't have a value, so it is saved here. And if you use the main function int main with arguments between parentheses, this is all saved here in this area of the memory. If you use a pointer int star values inti, so these are variables, so it is saved in the stack. Okay, if you have this values equal whatever, okay, so this is a function called malloc, and this is a system, this is a system call, one of the uh, functions. It uses a system call, so it is there in the heap. So this is an example how your program in C language is saved in the memory. Now we have uh, the processes once it is executed. So there is we save the state of the process. So once it is saved, we can have different states, like new state. It means that the process is created. Running, it is being executed. Waiting state, it is waiting for some event to occur. And ready state, and also terminated state, that it is done. Okay, finished execution. So we can draw this diagram to show you how it might start, initiated by new, now ready, and then waiting for something, running. Okay, if it is finished, that's it, go exit and terminate it. If it is not yet, so it create more interrupts, and it continues working in this uh, continue working in the program. So program continue running. It depends on your execution. But this is a simple diagram just to tell you how the flow of the process states can be done. Uh, Now we are having the data of every process, the data of every process, or the information. It is saved in something called the process control block, PCB, or they call it the task control block, or process control block. So whatever information we needed for any process, we save it, all of it here. So it is saved in memory. Okay, so we know we can keep tracking of every process, what are the data related to this process. So what is the main program, what is the program that it is related to, and the process number, the state of the process, the registers, memory limits, list of open files, etc. So all of this kind of data, we save it for one process. Now, one process might have, it can be executed alone, single, يعني, process without any uh, without breaking any resources. We need only one stack, يعني the stack area, the register area, the data area, and the files area. All of this in memory. We have one piece of code. Okay, so this is an example here. Okay, we have like process 0, for example. It is having one area of memory to save data in registers and also in stack. If it is this case, one code, so we can say it is a single thread. So it executes only one single code is there. Sometime no, sometime every sometime your code here, it requires multiple stacks with multiple registers, as you can see here in this example. This example here, your code does not need only one area of stack and one memory area of registers. No, it requires multiple registers and multiple stacks. In this case, we can say that your code here have multiple threads. So now imagine this big rectangle here or big box. This is your program, and your program has only two processes. Process 0, it has single thread, and process 1, it has multiple threads. So this is the scenario, what happens in your program. Now, in the lab, I believe you have some exercises you can do to practice these kind of things inside the lab. If you have any, if you need more explanation about a process and a thread, this is a video YouTube. You can see it. It will give you more understanding of how it is related to each other. Right. Now this data, the data that is saved in the this one, the process control block data. Okay, it is represented in Linux in this way. Okay, it's the same, the same representation. They have it here in Linux in this way. So all data in Linux, they have it the process ID. Okay, they call it T_PID. The state is saved here in state, and the data value is long. Okay, and this is the time slice, and this is the parent pointer to the parent process, and this is the child process, etc., etc. Right? So this is how this kind of data is saved using C language in Linux. Now, all these processes require scheduling in order to maximize the CPU, maximize the CPU utilization. So the process scheduler, if you remember from first classes, we were talking that the operating system has a process scheduler, it has a memory scheduler, etc., etc. Our managers. So this is a process scheduler. Select the processes for next execution on the CPU. So the scheduler select what processes to execute. So it has a scheduling queue. A queue is like a list of processes one each every time it will execute one at a time. So we have a ready queue and a waiting queue. So every process they in line to be executed one by one. So one line of processes we call it the ready queue, ready for execution يعني. And the waiting queue, which is wait until they for some reason, maybe they are waiting for some resources to come, etc. Right. So it is represented in memory in this way. So it is like a linked list, if you remember the linked listing data structure. So these are the process control blocks for multiple processes. This is a ready queue, okay, and this is a waiting queue. So this is how it is organized in memory. Now once the ready queue we have multiple processes, it's the scheduler, the CPU scheduler take the process, the ready process, and send it for execution to the CPU. Now the CPU will see what are the instructions. Does it require input output request? Does it have a time slice changes? Does it create a child process? Is it waiting for any kind of interrupt? So the CPU then go and execute whatever required accordingly. Okay, and then it go back. Once it finishes, it go back to the feedback comes go back to the ready queue. So this kind of the CPU then uh, have something called a context switch, so that it can switch from one process to another process. And this happens because the CPU is very fast and the I/O devices are very slow comparing if you compare it to each other. So what happens is sometime if process 0 here, it is executing, and then in one step here we need a system call to save the state into the process controller block 0. Once we want to save, then the CPU will be idle. Idle means the CPU is waiting and have nothing to do. So what happens is, instead of keeping the CPU not doing nothing, what we can do is we bring in process 1. So we utilize this free time and we execute part of process 1. So this is in order we utilize the operating system. The CPU. So the operating system, he manages and he schedules the processes, but in a way to make the CPU always busy. So there's an execution time here, and there is an execution time here, and the operating system makes sure maximum utilization for the CPU. And if you notice in the middle here, once we want to execute P0, we have to save the state into the process control block. We not need to update the data for this process to say, okay, it is in execution. And if we want to reload the state from the process control block 1, then it reloading require, for example, executing in the process P1 and so forth. So it comes here and here, So it's like you switch from P0 to P1, okay? the execution. So who manage this switching? The operating system. Who execute? Who do this switching as a hardware? The CPU. طيب. Uh, okay. Uh, okay, this is also clear. So the operating system must provide mechanisms for process creation and termination. طيب. Now we have the concept of a child and parent process. And why we need this? Because your program during execution, it requires uh, it requires being executed in steps, and during execution you need every piece of the code to be executed by the CPU. So every piece of code, once it is executed and finished, then you go back to the other piece of code. And this create a form of a tree, you know. I will show you a simple image here like this one. So for example, your code will start in some step here, process ID 1, and then it goes uh, to some other process. Okay, process ID, for example, here 8415, or here another process 8416 or 9296. So it goes splitting here as processes. So this is a child and this is his parent. This is a child and this is his parent. So this example, this is for a big program. يعني this is a example of Linux processes, which is يعني every one of them is a huge program. In Windows, if you go to the task manager here, in Windows, if you go to the task manager, you can have a list of processes. As you see here, we have the background processes, and every process here, you can have the how much of CPU, okay, it is utilizing, how much memory it is utilizing, the disk and the network. It will show you how much in the inside Windows. In Linux, it's the same. But and then also there are some processes related to each other. And for example, where is that one? Yani if you open this one, for example, you can say, for example, McAfee Web Advisor, okay? And then you will find that the McAfee Web Advisor as a service. So this is a running service, okay? But it is related, and this service is split into multiple processes. So you have one process here, you know, one here and one here, one, two, you know, three things, okay? Uh, Also, if you go to Microsoft Edge, okay, if you open it, then you'll have multiple things. You see, this is how they manage it. Chrome, where is Chrome? Mm, where is Chrome? ABC. Anyhow, etc. So you'll have every program has its own application. It has its own processes split into multiple processes. Okay, so this one, for example, is a huge one, a big one. I'm running Visual Studio. Okay, it has 17 processes, etc. So any program running, it's split into multiple processes. This is the major thing. Uh, uh, yeah, one thing here is once you want to terminate or finish a process, then there is also something called, yeah, yeah, this is the, yeah, click on details. You see here Chrome, we have many Chrome things. Why I have many Chrome? Because I'm opening many pages in Chrome. So if you see my computer here, I have this 1, 2, 3, 4, 5, 6, 7, many. I am opening many Chrome pages. So in Chrome, they open for every uh, tab, for every page, they create separate processes in memory. So I can right click here and end task. So this task is over. Or I can click on end process tree. So it means that it can have a tree of many things executed together. So anyhow, every process, it can be consist of trees, depend on what type of code it is inside from inside. Right. And every process, it has a specific ID. It is called process identifier, PID. Uh, the parent and the children share all resources. Okay. And we said always that when we mention resources, CPU, RAM, IO, etc. Right. Children share subset of parents' resources. Okay. Or parent and child share no resources. We have these three alternatives or options. It depends on your program, but all of it you can do it. Uh, During execution, parent and child execute concurrently, at the same time, or we have parent wait until the children terminate. Okay, so this kind of for type. How we can do it in operating system in Linux and or Linux Ubuntu, we have, or even Unix, they have the same the same commands, the same functions. So we have a fork system call create a new process, and the exe execute, okay, system call used after fork to replace the process. So, and then we have the wait. It means wait for the child to terminate. So if you notice here in this diagram, we have the parent. Once the parent is created, then you have a process ID created. So PID, it is a value, a number. You save in it the parent ID. Once you create fork, you call the function fork. In memory, it will go and create for the parent a specific ID. We don't know what is the ID given by the operating system. We don't know. So the operating system control it. It will give you, okay, this is the number for you in memory. So a PID, it's some sort of number, but it is not zero. Since the parent, the PID is not zero, then there is a process running in the memory. If we have the parent ID is zero, PID is zero, then it is a child. Okay. And it keep up, if it is waiting, then the parent resumes, it might go for here execute, and then exit, if it is a child, and so on. This is an example of a program. I believe you should have already taken it in the lab. It's just a small program that will create the fork here, fork a child process. So when you say PID equal fork, what does it mean? It means that you already in the parent, which is the main function here. You are already here in this big block. You are in the parent, and you want from the parent to go and create a child process. So this process will be part of the parent. Okay, so this is the example here. Okay, so you want to do some execution. Okay, طيب. Um, if you want to delete the process, you want to delete, you use exit system call. Exit system call. Now, sometime if the child process has exceeded allocation of resources, or the task assigned to child is no longer required, or the parent is exiting and the operating system does not allow a child to continue if its parent to continue. In these cases, you can use a system call abort. Okay, abort is like you finish but unsuccessful. Not like exit. Exit is like finishing with a success. طيب. Uh, okay. Now we have if a parent if no parent is waiting. Okay, if no parent is waiting, يعني did not invoke wait, we call a process a zombie. If parent terminated without invoking, okay, then the process is an orphan. So these terminology a little bit, I know, new for you, but by time when you practice in the lab, inshallah, things will be more clear for you, hopefully. طيب. Now I will skip this. This is an example I was telling you about the Chrome. In every tab in Chrome, when you open it, it means it's an independent process. That's it. Yeah. Okay. Now we have a terminology here called IPC. IPC. This is also very important on operating systems. And simply it means that every process can communicate with each other. They can cooperate. They can transfer data and receive data. They can send messages to each other. And communication and messaging and events handling, all of these terminologies are very important in the modern operating systems. So any process, it can be independent or it can cooperate, okay, with other processes. It can be affected by other processes, uh, and it can share data or information. Okay, it can also uh, uh, help in speeding up the computation, modularity and convenience. It will be, the system would be more convenient. Right. So we have two models of IPC, two models of inter-process communication: shared memory and passing. Message passing. So there are multiple processes sharing the same memory. Or we have also another way to do it is the message passing. So this diagram here, it will show you an example of the two. So we have طيب. We have, for example, process A, and this process, it sends data, it saves data here in this memory. At the same time, process B can any moment read data from the shared memory. Also, they can write data. So process A can write data in the shared memory, and process B can write data in this shared memory, the same one. So from here, okay, or you can go from here to here. So you have the same kernel, okay, running, and this is a RAM, as we always say, when we say memory, it means RAM. And we have this in the middle, a shared memory. So they can, both processes, both code, they can run at the same time and have access to this memory. So this is shared memory. The other one is messages passing, and this is the other communication model in the operating systems. Communication model. We have process A, so they send a, and process B. For example, process B send a message, so it is saved in the queue here, M0. Suppose process, so if we say, for example, 0, message 0. Process A send message 1. So first message 0 is saved from process B, and then message 1 is saved from process A, and then message 2, maybe it will come from process B again, and then maybe message 3 come from process A, and so on. So every new message comes, it is saved in a queue. So there is an order. Now, what happened also is not writing messages, but also reading. So this is a sharing also is in some sort of. So process B can read any of these messages in the queue, and process A can read any message from this queue. But it is a queue, يعني it should be serial, one by one. Okay. So these two models of communication, it can happen to collaborate or to cooperate. The processes can cooperate together. Right. This is also can have the same sharing of information. We have something called a producer-consumer problem. So a process can produce information, and another process can consume information. So sometimes the buffer is unbounded, yani we don't give limits. So no practical limit for the place where we save this information. And the other case, no, it is bounded. We have to specific to put a limit for the memory. So this concept also it's some sort of cooperating, but we look into it from another perspective, uh, like as I said, one process produce and the other process consumes. These examples here, these two examples in A and B, uh, process A and process B, they both have the uh, ability to produce and consume in the same time. A can save data here, and it can read data. It can write and read. Process B, it can write and read. Here also in the messaging, they can read and write. All the same. But in our scenario here, producer consumer, no, one process, it can write, it can create information, it can save information, but the other process, it consumes it, it only read it. And in this scenario, also we have more options. Uh, we have a limited or bounded buffer, or limited memory or unlimited memory, unbounded buffer. طيب. Whatever the options we said before, if it is sharing or it is messaging or it is consuming, producing, whatever these kind of things happens, it's all sort of communication, processes communication. Now, an area of memory shared among the processes that wish to communicate. This kind of memory, it must be available all the time for everyone. Now, if there are more users, uh, if there are more users, then it might have lack of resources. So the shared memory is limited at the end. Your RAM is limited. So you need have to synchronize the actions of these users, not to cause any lack of resources in memory. So this synchronization details will be parts of chapter 6 and 7 inshallah. طيب. In IPC, we have two operations to send and receive messages. This is the how it is used in Unix or Linux. As I said, it was يعني, I will not take much of time here. I want to skip it, this one. This is just a simple example how to create a link. طيب. طيب. Send and receive the same thing. Okay. Okay. طيب. Okay, I will skip these to here. Okay. طيب. I'll give you an idea about pipes now. Just simple idea, and then we close today's class. Okay. طيب. The pipes acts as a conduit. A conduit is like a canal, you know, like this one. You know, it's a canal, an area where these processes get in and out. So pipes, you want all processes to go through this pipe in order to they work together. So there is like you know, a road or a highway where the parent parent process can go through this pipe here, and then another process will go back through this pipe here. Okay, so this concept it is important to understand that sometimes we don't need uh, the uh, data to be transferred in one way. One way, it means unidirectional. We need it to go in two ways, bidirectional. Uni, it means one way, and bidirectional, it means goes in two way. As we said, it's like this is a road, and suppose data is going only one way like this. All data is transferred like this. All your instructions are going from left to right. But no, we need pipes. So the mechanism of pipes is like I have one way. I can transfer data and instructions this way in this sense, and also I need it to go in this way, in the same canal, in the same conduit, you know, in the same road. Okay. And you can implement this uh, in computer We name it in Linux and Unix pipes. And this is important for having a better communication. So the pipe concept, it allows communication, okay, and it is mostly important for the producer consumer style. Okay, as I was saying a minute ago, we have the one process is a producing information and another process at the same time is consuming. Uh, so the producer write to one end, the right end of the pipe, and the consumer read the other end, the read end of the pipe. So it become bi-directional. The ordinary pipes are unidirectional. This is the ordinary one, okay? But we need bi-directional, okay? That works in two ways. In Windows operating system, calls calls it anonymous pipes, okay? This is what they call it. Anyhow, طيب. Uh, so we have the concept of named pipes, okay, and we have the where they are more powerful than the bidirectional ones. So we have no parent-child relationship is necessary between the communication processes, and we have several processes can use the named pipes for communication in Unix and Windows, and also in Linux here. Unix, Linux, and Windows. Right? So these named pipes give you the facility without the need of a parent-child relationship. This is the most important thing about the named pipes. So communication is bidirectional, يعني in two ways, okay. Plus it is no parent-child relationship. So if you come here, so we have three concepts. The ordinary pipe. The ordinary pipe is unidirectional. This is the ordinary. The ordinary is unidirectional. Okay. The bidirectional with parent-child relationship, it is this one. Okay. Right. This one. In Windows, they call it anonymous pipes. And the third thing is named pipes. Named pipes, it is communication is bi-directional, plus no parent-child relationship is necessary. So this is the major two things about the named pipes. So these are the different types of ways how to processes are communicating through in Linux, Unix, and Windows. Hopefully this class was clear, inshallah, for all of you, and good luck for everyone. طيب, I'll send you the link for attendance. I forgot the attendance. You can fill in the attendance link and then you can leave, okay? I will stop recording.